lecture, we have started with differential amplifier. So we have seen why we require differential amplifier, how it is different than single stage amplifiers, and we have seen its terminology. Now we'll go for the working of differential amplifier and its DC transfer characteristics. So that is the objective of this lecture. So let us begin. So we'll start with the topic of, please draw the basic differential amplifier circuit diagram. The basic MOSFET based differential amplifier. Okay, MOSFET based differential amplifier. Now let's draw that circuit very patiently. So we have, first we take the MOSFET like this. Now we mirror image the MOSFET here. Okay. Now we connect a drain resistor in both the places. And at the gate terminal, we apply the inputs. So one input will go over here. So along with the input, we can also show its source resistance, but right now for simplicity, we can avoid it. So here is my second input. So input, I'm calling it as V1 and V2. So remember, V1 and V2 are my AC inputs. Okay. Now, here is my power supply, positive power supply. So here we will have a source resistor and a negative power supply, VEE. This will be, we can call it VSS, sorry. This we can call it as VDD, and this is VSS. This is RS, this is RD1, this is RD2. Please complete the diagram. Then I'll discuss about it a little more. Okay, we can name the transistor as M1 and M2. Okay, M1 and M2. Okay, here we will consider DIBO configuration. So that means the outputs are balanced. So here is my VO1, this is VO2. So where is my output actually? Output is across this plus minus V out. Acha, you can consider why we have written plus over here and minus over here. You can do reverse also. It's fine. Only thing is the output will be negative. That's it. So this is my complete diagram of MOSFET differential amplifier. That is dual input balance output MOSFET differential amplifier. Okay, completed. Students, yeah. So
Yes, sir.
remember, earlier we have studied single stage differential amplifier. If you remember correctly, there were three external capacitors. Now here in this MOSFET differential amplifier, you do not see any capacitors connected. Yes or no? And now we'll study why even without the capacitors, it will still amplify the AC signal, the difference between the two AC signals input. Okay, now we'll add some more details in this the same diagram. Let's add the details over here. So the current flowing through RS, we can call it as IQ. Okay, this current at this terminal we can call it as IS1, IS2 because that is the source terminal. Yes or no? So this is IS1, IS2. Let me highlight the terminals. So this is gate number 1. This is source 1. This is drain 1. Okay. This is associated with transistor M1. This is drain 2, gate 2, source 2. Got it? Yeah. Current flowing through resistor RD1 will be ID1. Current flowing through RD2 will be ID2. Okay. And you remember in a MOSFET, no gate current flows. So ID1 is actually same as IS1 and ID2 is same as IS2. All right. Are you following? Yes or no? You have written these things?
Yes.
Okay. So can you write over here what is IQ? So if you apply a KCL in this node, so outgoing current is IQ, incoming currents are IS1 and IS2. So can we write IQ is actually equal to IS1 plus IS2. And what is IS1? Source current flowing through the source terminal 1 of M1 transistor. So which is same as ID normally is same as IS. So can we write it as IQ is ID1 plus ID2? Yes or no? Okay. So you have understood this step number 1. All right. There are certain assumptions while we proceed further. So let's list down the assumptions. So assumption number 1 is here the value of the resistor RD1 is matched to the resistor RD2. So they are same mostly. Drain resistor RD1 and RD2 are same as RD. Then we consider the transistor, the MOSFET M1 and M2 are matched. We consider M1 and M2 to be matched. What do you meaning of matched? Their threshold voltage is same. So VTN1 is equal to VTN2 is equal to VTN. Okay. And secondly, their Kn is same. When we say a transistor is matched, that means its threshold voltage is same and its transconductance is same. This is device gain Kn1 and Kn2 is also equal to Kn. That is the meaning of the word matched. Okay. Yes. So these are the assumptions. Any doubt anyone so far related to this configuration? Hello? You're following what we are doing over here? Yes or no? Hello? Any feedback from anyone? You have any doubt? Or can I
No, sir.
proceed? Okay, all right. Yeah. So now you see carefully this M1 and M2. We have seen that earlier for a transistor to work as an amplifier, my MOSFET should be operated in the saturation region. Agree? That means for this differential amplifier also, your MOSFET should be working in the saturation region. And so what is the saturation region? M1 and M2 should be in the saturation region. That means if this is my device characteristics, it should be operated in this region. Remember this region? This is output characteristics of MOSFET. So it should be operated in this region. Agree or no? Here RO is also present because we have a slope over here, right? Correct. So your MOSFET should be operating in this saturation region. That is also one of the assumptions which we have to make. So this is point number C. Or else your transistor won't contribute towards amplifier application. Your current should be steady. So what is the important thing? What is the important thing of being as an amplifier? So both, I mean, in the saturation region, so both M1 and M2, which are NMOS transistors, are delivering constant current almost. So it's acting as a delivering or passing through, we can say. Both transistors are carrying almost constant currents. Yes or no? In response to VDS voltage. Okay. Both transistors are passing through constant currents. Yes or no? Now, when the currents will change, this current magnitude will change when we change the value of VGS. Correct or no? This is VGS1, VGS2, higher value, right? So if we reduce the value of VGS, the current level will come down. If we increase the value of VGS, the current level will go up. Are you following? But if we keep VDS value same, the current is almost straight line. Did you understand this fact?
Yes.
Okay. So let me start with now. I will formally start. How this will work, I will explain when I complete the DC transfer characteristics. Now just believe in the derivation steps, and then when the derivation step is complete, after we have drawn the transfer characteristics of MOSFET, then I'll explain the working again. Don't worry. So far, this is what is happening. You're applying two differential input signal, dual inputs, and we are taking the balanced output terminals, drain 1 and drain 2. The current ID1 and ID2 flows, and let's see what happens now. And M1 and M2 has to be in the saturation region. That means they are carrying the almost constant currents. So here we also assume that transistor M1 and M2 are matched, and we assume that both M1 and M2 are biased in the saturation region. So this is one of the assumptions only. So the basic MOSFET differential amplifier uses both positive and negative bias supply. So this is the clue actually. Because of the positive and negative power supply, it eliminates the need of any coupling capacitors or voltage dividing biasing resistors. As you can see, there is no voltage dividing resistors also externally connected. So this type of amplifier is called as directly coupled, directly coupled amplifiers, which does not require biasing resistors. So no need of number one, capacitors, coupling capacitors, and no need of biasing resistors. Yes or no? That is why this configuration is more famous in case of integrated circuits. Okay, understood? Now, tell me what is my differential input for this amplifier configuration? What is differential input? VD or VID in this case? Is it V1 minus V2? Yes or no? Hello? Agree
Yes.
or no? Ha. Now we our derivation for DC transfer characteristics will start. DC transfer characteristics. So derivation starts from here. Okay. So what we do is we neglect the output resistance. So we neglect the RO, output resistance of M1 and M2, and assume that two transistors are matched. So what do you mean by two transistors are matched? See, you remember the drain current equation of the MOSFET ID1 is given by what formula? Kn times VGS minus VTN. Yes or no? VTN1 the whole square. VGS1 minus VTN1 the whole square. Do you agree on this? Come on, this characteristics. This is ID versus VGS characteristics. So what is this equation given by? Remember, ID is equal to Kn times VGS minus VTN the whole square. Did we write this before? Yes or
Yes.
no? Huh. So same equation we are rewriting it over here. So basically what are we saying? ID1 is proportional to VGS1 square. ID2 is proportional to VGS2 square. Meaning any small change in VGS, it will lead to a large change in ID. Agree? A small change in VGS over here, a small change in VGS over here will lead to a large change in ID, as you can see from here. Yes or no? So, but we have said that VGS1, VTN1 and VTN2 are same. So we can write over here VTN1 is equal to VTN2 is equal to VTN. Okay. So ID1 is equal to Kn times Kn1 we write, right? Kn1 is equal to Kn2 is equal to Kn. So we have written over here ID1 we rewrite it as Kn times VGS minus VTN the whole square. So this we call it equation number 1. Similarly, I hope you're writing along, and ID2 is equal to Kn times VGS2 minus VTN the whole square. That is equation number 2. Written so far. Now a little bit of mathematics will come. Now we take the square root of equation number 1 and 2. Okay, we take the square root and subtract 1 and 2. We get, let's do that. So we write square root of ID1 minus square root of ID2. So when we take square root, what do we have over here? Root of Kn, right? It's common. Yes or no? And VTN gets cancelled. Do you agree on this? Or you want me to skip the steps? Only VGS1 minus VGS2 remains. Agree? Yes or no?
Yes.
Hello. Acha. Now what is VGS1 minus VGS2? Can you tell me? Acha, let us bifurcate this. What is VGS1? VG1 minus VS1. Correct? What is VGS2? VG2 minus VS2. So what will be VGS1 minus VGS2? That VS1 and VS2 are same. Let's go back to the diagram. Here it is. This is VS1, this is VS2. They both are the same, right? So we can write VS1 and VS2 are same. So we can write VGS1 minus VGS2 is equal to VG1 minus VG2. And what is VG1? Can anyone tell me? V1. And what is VG2? V2. Correct? So we can write it as that is equal to V1 minus V2. Agree? And what is V1 minus V2? Differential gain, differential voltage. So can we rewrite this expression as follows? It is square root of, this equal to square root of Kn times Vd. So this is equation number 3. Yes or no? Agree? Where we can write where Vd is given by VGS1 minus VGS2, which is equal to V1 minus V2. And this is called as differential mode input voltage. Okay. Vd is called as differential mode input voltage. Okay. So if this differential mode input voltage, are you understand? Have you completed up till this step? Yes, no, what?
Yes.
Okay. So now if this differential mode voltage, let's go to the next step. Step number, I think 4 or 2. This is 3. This is 4. This is fifth one. If this differential voltage is greater than 1, that means what? Can I say V1 is greater than V2? Yes, no? And can I say VGS1 is greater than VGS2? Yes or no? And because of this, can I say ID1 is greater than ID2? Agree? Yes or no? If differential voltage is non-zero, that means V1 has to be greater than V2. That means VGS1 has to be greater than VGS2. That means ID1 has to be greater than ID2 because ID and VGS have a square relation, right? So if VGS changes, the ID will change drastically. And we have seen that over here. Okay. For a small change in VGS, there is a large change in ID. So over here, the current flowing through M1 transistor is more than current flowing through M2 transistor in this case. Yes or no? Now, acha, what was from recall from equation number one? What was equation number one? Sorry, this step. A we write it. Equation number A. IQ is ID1 plus ID2. We'll write that now. Step A. So we write IQ is equal to ID1 plus ID2. Correct. This we call it equation number 4. Okay. So how much is ID2 from here? It will be IQ minus ID1. Yes or no? Correct. Now let's check equation number 3. So we'll write from equation number 3, it is what? Square root of ID1 minus ID2, right? So square root of ID1, instead of ID2, we'll write it as this term. It is IQ minus ID1, correct? Is equal to Kn times Vd, root of Kn times Vd, right? So what we'll do is we'll square both the sides. So Kn times Vd square will write. So here what we did, squaring both sides. Did you understand what we did? So here we are just subtracted. Now we squared it also. So k root of Kn times Vd becomes Kn times Vd square. Here it is. And instead of ID2, we substituted it as IQ minus ID1. Understood this? Yes or no? Now what is this A minus B the whole square? So A square will be ID1 minus, minus what will come? IQ minus ID1, then minus 2 AB. So 2 root of ID1 root of IQ minus ID1. Agree? Is equal to Kn times Vd square. What will get cancelled? This is, I think, plus A square plus B square minus 2AB, right? This will be plus. What gets cancelled? Tell me. ID1 gets cancelled? Yes or no? So inside the bracket, what do we have? Square root of ID1 into IQ minus ID1 is equal to, this 2 will come over here, right? So it will be half this IQ minus Kn Vd square. Do you agree on to this term? Equation number 6. Do you follow this? Yes or no?
Yes.
Okay. Now what we do is we again square. Squaring equation number 6, we get ID1 square minus IQ into ID1. I have opened this bracket is equal to what? 1 by 4 IQ minus Kn into Vd square, the whole square. Yes or no? Is this proper, right? This is minus or plus? This is, yeah, IQ minus. Yeah, it is correct. Now what do we do? Next step will be, this is point number 7, I guess. Oh, wait a second. Now this will be in the quadratic form. So it is ID1 square minus IQ ID1 minus 1 by 4 IQ minus Kn Vd square the whole square is equal to 0, right? This we call it equation number 7. Okay. So this is quadratic equation. So we apply the quadratic formula and rearrange the terms. We note that ID1 is greater than IQ by 2, and VD is greater than 0. So these two are the assumptions. So do you remember this formula? Root of minus B plus or minus square root of B square minus 4AC upon 2A. Do you remember these roots? Yes or no? So it will be IQ by 2 plus square root of Kn times IQ by 2 into Vd square root of, you don't have this entire derivation, but without this you won't understand a thing. So that's why I'm doing the derivation mostly. But if they ask you in the exam, draw the DC characteristics and explain it, you have to write few steps. So that's what I'm writing over here. This is equation number 8 by solving in with this matter, this technique. Okay, understood? So similarly we can write, similarly ID2 will be equal to IQ by 2 minus square root of this term. Again the same term will come, IQ by 2 into Vd square root of 1 minus Kn upon 2 IQ into Vd square under root of. This is equation number 9. Okay, this is very, very important. Now what we do is we normalize the drain currents. How do we normalize the drain currents? Write down. Next, normalized drain currents. Meaning what do we do now is we do ID1 divided by IQ, and here we will do ID2 divided by IQ. So what do we get over here? IQ we take it common, right? So what do we get over here? ID1 divided by IQ will be equal to half. This will become half plus square root of, here if we take ID1 common, it will go down in the denominator. So it will be Kn divided by 2IQ into Vd square root of 1 minus Kn twice IQ into Vd square. That is what we get. And what will be ID2 divided by IQ? It will be half minus this term, same term will come. Kn upon 2 IQ into Vd into square root of 1 minus Kn upon 2 IQ times Vd square. Okay, so these are equation number 10 and 11. So please complete this much. Complete this much, please. Okay, and write down this equation number 10. I mean, this equations will represent equation number 10 and 11 describes the DC transfer characteristics of MOSFET differential amplifier. Okay, so please complete this derivation. I'll just come back in 2-3 minutes. Yeah, I'll be right back. Hello. Hello, students. Hello. Students, you are there?
sir.
Acha, yeah. Sorry for the disturbance. I'll continue now. Uh, you have written up till this equation number 9 and 10 and 11. Now, this equation number
Yes.
10 and 11 describes the basic DC transfer characteristics of MOSFET differential amplifier. So, if you feed these equations in a computer and if you try to plot the graph of VD versus ID1 upon IQ and ID1 upon ID2 upon IQ, you will get the graph like this. Please draw this graph. This is the transfer characteristics of MOSFET differential amplifier. So we'll draw at the center only like this. Let me try to draw a straight line. Here it is. And x-axis we have differential input. Okay. Let me draw this side properly. Okay. So this is my differential input VD. Okay. And on the y-axis, I have my normalized output. So how the graph will be? Let me draw the graph and show it to you. So the graph will be like this. Okay. And on this side, it will be on the same lines here. Start from here. Here it is. This how the graph will be symmetric across this point and this point. Okay. So this curve will represent ID1 divided by IQ, and this curve will represent ID2 divided by IQ. Normalized currents, because we have divided current. So this will be just numbers, ID2 divided by IQ. All right. Let's say this number is 0.5. This number is 1. 1 means ID1 and IQ are same. So please draw this graph. And here the numbers are, let's say, 0.2, 0.4, 0.6, zero point 0.8, and so on. This is minus zero point 0.2, minus zero point 0.4, minus zero point 0.6, minus zero point 0.8. Okay. So this, let's write the heading of this. This is called as normalized DC transfer characteristics of MOSFET amplifier. MOSFET differential amplifier. It's a normalized DC transfer characteristics of MOSFET differential amplifier. Did you understand the meaning of normalized? Normalized meaning ID1 upon IQ. Okay, so it will be just a number. So it can be 1 when ID1 and IQ are equal. Okay, fine. Completed this. So this curve is also same. This curve is also ID1 divided by IQ only. This curve. And this curve is also ID2 divided by IQ. Please draw this graph. DC transfer characteristics. Have you completed?
Yes.
Okay, great. Now listen to the entire working of differential amplifier from this graph. Now, before we move ahead, can you see this? This is a linear region, dotted line if I draw like this, and here also. What do you mean by linear region? Can you see these lines are straight, constant? Yes or no? See, this line is almost a constant, right? Yes or no? And this line is also constant. Agree? Almost a straight line. That's why it's
Yes.
a linear region. Yeah. That's why it's a linear region. So mark this region as linear region. Linear region. And remember, every point of time, IQ is ID1 plus ID2. Okay, don't forget that. And let me draw the small version of differential amplifier over here and explain you the working. And this is the supply. ID1, RD. This is output. Okay, this is small mini version of differential amplifier over here. This is plus minus V out. Okay, this is M1 transistor. This is M2 transistor. Agree? Okay, so this will be the current ID1. This will be the current ID2. Okay, now listen carefully. Are you listening? Everyone? Okay. Acha, what do you mean by VD positive, VD greater than 0? Can I say V1 is greater than V2? Yes or no? So can I say VGS1 is greater than VGS2? And can I say ID1 is greater than ID2? Correct, no? If VD is what? VD is given by the differential voltage gain will be given by V1 minus V2. Correct. So that means if the differential voltage is positive, that means V1 is greater than V2. That means V1 voltage is greater than V2. That means VGS1 is greater than VD2, VGS2. That means drain current ID1 is greater than ID2. That means M1 is more into saturation. It's a saturation. deeper into saturation. It flows, heavy current flows through M1 compared to ID2. Yes or no? When VD becomes positive, more ID1 current is more compared to ID2. As you can see, when VD2 is become positive, VD2, VD is becoming positive. Yeah. So differential voltage is positive means what? As you can see, current ID1 is always more than current ID2 in this region. And as the differential voltage increases further, my V1 becomes more and more greater than VGS2. That means my current ID1 becomes more and more greater than ID2. And don't forget, see this here happening, here this is happening. ID1 is increasing, ID2 is decreasing. So when the difference between V1 and V2 is too large, that means at this point of time, that means at this point of time, we can say, and this point of time, M2 is almost off. Why? Because entire IQ flows through only ID1. ID2 is almost going to zero. As you can see, and here it is, M1 is fully on. So M1 is carrying all the current. So transistor M1 is on and M2 is fully shut off. Agree? Students, you are saying yes or no?
Yes.
Huh? Yeah. So this here, the M1 transistor carries entire current in the circuit, and M2 transistor is almost off, saturated. Okay. Now let's go back to this case. So in this case, differential voltage is less than zero. That means V1 is less than V2. That means VGS2 is greater than VGS1. That means ID2 is greater than ID1. Okay. And now let's write this equation. IQ is ID1 plus ID2. So as soon as the differential voltage is negative, what happens? Transistor M2 conducts more compared to transistor M1. And when the difference increases, when V2 is much greater than V1, VGS2 is much greater than VGS1, so ID1 dominates. And at one point of time, M2 is fully on. So here at this point of time, M2 is fully on. And here M1 current becomes zero almost. So M1 is off. Agree? Yes or no? So these are the points which we are discussing. So over here we have M2 on, M1 is off, and here M1 is on and M2 is off. Yes or no? But do you see this linear region? So what happens over here in linear region? In linear region, almost one current is greater than the other, but both the transistors are on over here. Here in this case, and almost linear current flows through the circuit, a predictable current. So the differential amplifier will work perfectly within this linear region only. Beyond the linear region, what will happen? One transistor will operate more than the other transistor. Yes or no? So the transistor will deviate. That means more current flows to one transistor, less current flows to other transistor. So as long as differential amplifier, the difference between the two signal is small, the differential amplifier will work perfectly well. As soon as the difference between the two signal is large, then only one transistor is on and other transistor becomes off. Then it stops working in the as a differential amplifier. So only in this linear region the differential amplifier works as a differential amplifier. Okay, only when the difference between the two signal is very, very small. As long as that happens, then only it works as a differential amplifier. All right, understanding? So here in this range, we can say differential voltage is V1 minus V2, which is very, very close to zero. That means V1 and V2 are almost same. And here we can assume ID1 is almost equal to ID2. They are at almost similar levels. Let's say one is at 12 milliampere, other might be at 10 milliampere. So only within this linear region, the MOSFET, whenever differential amplifier work in the linear region, both the transistors are on. And ID1 is almost equal to ID2, which is equal to IQ. All right. Understood this? Students. So this is the working of differential amplifier from the transfer characteristics. Understood or no?
Ah, sir.
Huh. And from this equation number 10 and 11, we can see that at a specific value of differential input voltage, the bias current IQ is switched entirely to one transistor than the other. As you can see, as you go on increasing the difference between the differential input signal, one transistor carries entire current, whereas the other transistor carries almost no current. That means it is off. Here in this region, ID2 carries all the current and ID1 is off. Okay, understood this? So this is how your differential amplifier will work. All right. Now, next time we'll start with DC analysis. Now, let me summarize what we will do next lecture tomorrow so that you're better prepared. I'll share the handouts with you all. See, we have to do DC analysis of differential amplifier. Now, the good news is that DC analysis is same for all four types of DFAMs of differential amplifier. Okay, so you do DC analysis for anyone, it's same for all the four types of differential amplifier. Whereas AC analysis, for AC analysis, what we need to do is we need to investigate the value of AD. We need to find the value of AD expressed in ACM and CMRR. That is what we need to do. Okay, and that we have to do it for DIBO. So SIBO will be same, and then we have to independently do it for DIUO, and SIBO will be different. This will be same. This will be same. This two will be individually will be different. This is SIUO. All right. So that is what we'll do in the tomorrow's class. So that's all for today. You have any doubts, you can ask me. Let me stop the recording. Students, you have any doubts?